Hi, everyone, and welcome to Chapter 5, Distributed Forces, focusing on sections 5.8, 5.9, or section 6.9 of Chapter 5 from your textbook, are transitioning from learning about centroids to distributed loads. There are a lot of examples in engineering of distributed loads. Common cases I like to talk about are snow, wind, water, things like that. Weight can definitely be distributed over an area, so over a surface area or over a set volume. It's what ends up happening is it becomes convenient to represent the load. So this distributed load, we figure out its point force equivalent. A point force is like if you were to have a rope tied to something and you were to pull it, and it's only acting on one single point. It's what we've been working with up to this point, our point forces. So we can represent our distributed load as a concentrated point force located at the centroid of the distributed load. What that means is we're going to take the weight distribution, come up with a profile of that weight distribution, and we'll use that when we talk about area and distance. We're using them in a representative way when we look at this force profile. Distributed loads do not always act on the centroid, but they do when they're consistent non-variable weight distribution, which is what we're going to look at in this class. Distributed loads are forces that are spread out over a length, area, or volume. Load or weight density are other names commonly used for distributed loads or any combination of those words. Distributed weight, load density, etc. Most real-world loads are distributed, meaning the weight of materials, any material with a large surface area or volume, beams, that's the last thing, and what we're going to be focusing on are straight beams. But those are all distributed loads. Force of wind, water, earth pushing on a surface, snow I like to talk about up in New Jersey, a flat plate underwater, the side of a dam, the side of an aquarium tank, the side of an underwater window, the side of a window in a windstorm. Remember, wind and water have similar behavior for our hydraulics and pneumatics, right? Like I said, in this class, we're going to talk about beams as our transition into it. So here's our beam representation. We have an x-axis starting at O, going all the way to B of length of L. The weight distribution here, you can see by this profile. Technically, our distributed load, so our weight is going to be the area under the curve of that weight profile. To get that, we would integrate, just like how we talked about with centroids. We're not going to need to physically do all the integrations ourselves. Because they've been done, we have charts and we'll have them memorized. If you want, you can do them yourselves. But usually it's easier to just work with the information we have. Coda, it's okay. Let's look here though. The distributed load is represented by plotting the load per unit length. So each little individual area of this is going to be load per unit length, individual dx, infinitesimal length, dw, the infinitesimally small amount of weight being applied at that one particular surface area or that one particular area of length. Take the summation of all of that, the area under the curve is going to be equal to the magnitude of the point force equivalent, right? So W is equal to the integration from 0 to L of each of those individual values to get a total weight equivalent. And that is going to act at the centroid of that profile. In this case, because we're looking at a horizontal beam, it's going to be at the centroid. All of our forces are vertical forces, right? In my mind, distributed forces become much easier with application. Theory sounds a little more complicated than when we apply it. So here we have a beam that supports a distributed load as shown. Find the equivalent concentrated load and the reactions of the supports. First thing, find the equivalent concentrated load. So we said that the load is going to be the area under the curve. This is our profile. So at A, we have 1,500 newtons per meter. That is our minimum all the way across the 6 meters. So if we wanted to, we could cut off a rectangle. That could be our area 1 of this 1,500 newton per meter times 6 meter to get one area here. If that was all we had, if that was the only area that we had, that multiplication would be the magnitude of our force, and it would be applied at the halfway point at the 3 meters. But it's not all that we have. We have this increase up to 4,500 newton meters at point B. So what you could do is either separate it into that rectangle and a triangle, or you could separate it into two triangles, which is what we're going to do here. Triangle 1 is our bottom triangle. It has a height of 1.5 kilonewtons per meter and a length of 6 meters. The area for that, 1/2 area of a triangle is 1/2 base times height, 1/2 1.5 times 6. We're going to get 1.5 kilonewtons. For our second area, 1/2 base times height, 1/2 4.5 times 6. We're going to get 13.5 for the area of our second triangle. The magnitude of our force is going to be the area under that curve. So the magnitude of our whole force is going to be the summation of these. Summation of areas is going to be 18 kilonewtons, right? Kilonewtons per meter, kilonewtons by meter. We're multiplying that by meters. We're getting units of kilonewtons. That's our equivalent, our point force equivalent to that distributed load. That point force is going to be applied at the x-centroid of this hole. The easiest way to find that, the easiest way to find that is to use our centroid equation, right? Big X bar, or the x-centroid of the whole system, times the summation of areas is equal to summation of little x bar times A. So the x bar of triangle 1, the x bar of a triangle, or the x-centroid of a triangle, is 1/3 toward the largest edge. So it's going to be 1/3 times that 1.5 side times A towards A. So we're going to have 2 meters. For triangle 2, again, it's going to be 1/3 of the total length towards the longest side. In this case, the longest side is on B, so it's going to be 2 away from B. So if we're using A as our origin point, that's going to be 4 meters. Multiply each x-centroid by its respective area, sum those two together, and then divide that by the summation of the areas to get the x bar of the whole profile, which is going to tell you where that force magnitude is being applied to. So in this case, it's going to be an equivalent, this force profile is going to be equivalent to an 18 kilonewton force at 3.5 meters from A. We're not done there. We have to figure out our reaction forces. So A, we have a roller, a vertical force will be applied there. And B, we have a pin joint. So we're going to have a vertical and a horizontal force applied there, or an X and a Y. We can find the moment at A to find BY, and then use the moment at B to find AY. Alternatively, we could find either one of those and then use the summation of forces in Y equals 0 to find the alternative one. The last thing we'll have to do is the summation of forces in the X direction, which is equal to 0, which will give us that our reaction force at B, our Bx, is equal to 0. This example problem 5.10 is a lot more complicated than anything we're going to see in this class, especially anything on a test. But I just want to show how this concept can be easily made more complicated and used to have real applications. So here we have our reaction force at A or at AB is going to be, we're going to have a vertical and a horizontal force because there's going to be no sliding available. There's also going to be a rotational force because of that concrete fixture. Each area of this is going to have some weight distribution, right? This is all concrete, it's all going to have a weight pulling down on it. We can use the density to figure out what that weight is pulling down on each element. So slice this into profiles. We recognize a triangle, a rectangle, parabola. Then we have the inverse parabola of the water. We can find the weight of each of those areas And then we'll have a distributed load over on this side for our water. So there's a distributed load in each of these weight elements. Yes, there's also distributed load in the water hitting the dam, hitting the concrete. Remember that your depth and pressure have a relationship with each other. So this ends up being a problem that we really could, again, more complex and more steps than we talk about in our class usually, but something that we could take our concepts from this class and apply to. Here is the final workout of the problem if you are interested. But like I said, it's more just the understanding the concept. Let me know if you have any questions, and I'll talk to you soon.